I am Miss Hu, your physics teacher. In this video, we are going to go through the gas laws and the absolute temperature scale. Before we get into this, first things first, we have to establish how gas particles exert pressure. So what we're looking at on this slide is basically a container that's got some gas particles trapped in it. So the square here represents a container and the blue round circles represent the gas particles. So in this case, this is an airtight container, so no new gas particles can come in and the gas particles can't escape. Essentially, this means that the mass of the gas that's trapped inside this container remains the same. Now let's recall what we know about the kinetic theory of matter. All matter is made up of tiny, discrete particles that are constantly in motion. So when it comes to gas, we know that gas particles are constantly moving in random directions. So in this case, all these particles are constantly moving. Now, obviously, when they're moving, they're going to be colliding when they hit the surface or when they hit each other, right? So let's talk about how the pressure is exerted onto the walls of the container. Because these particles are moving, and when they hit the wall of the container, they're going to bounce off. So they're constantly colliding against the walls of the container. Now, if you remember what you have learned about impulse and impulsive force, impulsive force is the force that's exerted during collisions, which means that every time these gas particles collide with the walls of the container, they're exerting an impulsive force. Now, if you didn't learn the term impulsive force, you should anyway have learned that it's a force. So every time the gas particles collide against the walls of the container, it exerts a force. I'll write that down for you. Okay, so the gas particles collide against the walls of the container. The collision produces an impulsive force. Now, if you can remember what you've learned about pressure in general, pressure is force per unit area. So write that down, because I know some of you will be like, what? What did Miss Ho just say? All right, so pressure equals to force divided by area. So this is the general formula for pressure. Because the gas particles are producing impulsive force every time they collide against the walls of the container, it exerts a pressure because pressure is force per area. So basically, the gas pressure in this case is the ratio of this impulsive force per area of the walls of the container. So let me write that down for you because I know some of you have just what? Right, so gas pressure is the average impulsive force exerted by the gas particles per unit area. Okay, I know the text has kind of run off. I'll just readjust for you to be over here. And that's how gas particles exert a pressure. So this is important to understand because this will help you understand the gas laws on the next few slides. So let's look at one of the first gas laws. So in this case, let's examine a situation where the containers are of a fixed volume. So that means this container cannot increase or decrease its volume. And what we want to do now is we want to investigate how the temperature affects the gas pressure. So we're going to zoom in a little bit for us to see. Okay, so here we've got two diagrams. Actually, I want you to imagine in this case, these two are actually the same container. So situation one, that means before, and situation two, which is after. So before and after. So let's say we've got some gas particles that are trapped inside this container. And obviously, they're having the time of their lives by colliding against the walls of the container. Ta-da. Okay, now let's say we heat up this container with the gas particles inside. Okay, I'm going to just use my iPad because it's easier to draw. So there may be a slight delay in what I'm saying and what I'm drawing. Okay, so I want you to imagine, okay, before it's a little bit colder. Now, after situation two, Okay, we're applying some heat over here. So these red arrows represent heat that's being applied. I want you to think, when heat is being applied and the volume can't change, what's going to happen to those gas particles? That's right. Obviously, they're going to be moving a whole lot faster, right? So these gas particles, I'm just going to copy and paste them over here. Oh, I'm not supposed to move that. Go back, go back. All right, so obviously these gas particles are going to be moving a lot more quickly. So just to help you visualize the difference over here, I'm just going to draw some arrows. So here, obviously, there's going to be some collision. So these arrows represent the collision of the gas particles against the walls of the container. So when the gas is heated, the gas particles are going to be moving a whole lot faster. So I'm going to draw it in red just to show how fast it's moving. It's going to be colliding even more quickly. So the more collisions there are, the more force is imparted, therefore more pressure. Logical, right? So that means the greater the temperature, the greater the pressure the gas is exerting inside this container. So I'm going to write that down. The greater the temperature, the greater the gas pressure. So this is the relationship between temperature and pressure of the gas. It is in yellow just because, right? Okay. Now, you have to remember that in physics, it's not enough for us just to state this general relationship. Um, we also would do experiments, and based on the experiments, we look at the relationship and then we'll plot a graph. So, based on the person who has already researched this, they've already plotted the graph and all that. So, I'm just going to plot what the general graph looks like. Let's use another color just because it's interesting. So let's say we plot a graph of the pressure against temperature. Let's say, okay, on the x-axis, this is temperature measured in degrees Celsius, and this is pressure, let's say measured in Pascal, for example. Now, based on the experiments that were conducted, and you can even try this in the school lab under the guidance of your teacher, of course, you'll find that the graph obtained will be a linear graph. But the graph does not start from origin, so it will look like this. Now, here's the thing about physics. Although we like straight line graphs, we don't really like it when it starts in the middle of the axis. We like graphs that start from the origin. So how do we get it to start from origin? Well, first of all, we have to extend this graph to see what the value is on the x-intercept. So if we were to extend this graph, you'll find that the number, assuming it's a perfectly straight line, I know it's a little bit crooked, but it's a perfectly straight line, you'll find that the number on the x-axis here will be negative 273. Now, why? Because that's life, all right? So get with the program. So how then do we get a graph that starts from the origin? We have to change the values a little bit, and this is where a new temperature scale was obtained. So in this case, we shift the graph forward so that it can start from the origin. You cannot plot this against degrees Celsius, obviously, because the number should be negative 273. So this is then plotted against a temperature scale known as Kelvin. So Kelvin is a new scale that was derived from the degree Celsius scale based on this graph. And to get the value of Kelvin, we take the value of degree Celsius and add 273. So I'll just write that down for your quick reference over here. T, which is absolute temperature, measured in Kelvin. You take the theta in degrees Celsius at 273. And that's how we shift this graph from here to here. And in physics, we like this kind of graphs. We're like, ooh, it looks so pretty. Now it starts from the origin. So this is the relationship of this particular law. In this case, I'm going to write it out for you. The gas pressure is directly proportional to the absolute temperature. Now, of course, there are some caveats here, okay, provided, I'm spelling this wrong. Let me shift this because I know you can't see it, provided that the mass is constant and so is the volume, so that the mass and volume are constant of the gas, obviously. Now, this law is named after the researcher who discovered this relationship, and that's why this is known as the Gay-Lussac Law. And that's the first gas law. Now, there are three gas laws in general. We're going to go to the second one now. Let's say in this case, there's a situation where the gas is under the same pressure throughout. We change the temperature to observe the difference in volume. So let's zoom in over here. Let's say now we've got some gas particles trapped inside this container. In this case, this particular container can expand and can shrink. So like a balloon, the volume is not fixed. I want you to imagine now, if we were to take this container, I'm just going to draw a second one over here and put it aside. And let's say now we apply heat. I want you to think now. This is like a balloon. You apply heat. What's going to happen to the volume? Is it going to stay the same? Is it going to increase or is it going to decrease? That's right. The volume is going to increase. Let me put more gas particles here because it's just one instead. So yes, the volume of the container is going to increase as you apply heat. And this is another relationship of gases. So over here, I'm just going to copy and paste because I am lazy. Right? So in this case, the greater the temperature, the greater the volume of the gas. Similarly, to the Gay-Lussac law, the researchers who researched this, they can't just rely on the relationship. So obviously, they're going to be plotting graphs based on the data that's collected. So when they plotted the graph, so in this case, it rains degrees Celsius. We have volume, let's say in meter cube, plotted against temperature in degrees Celsius. Similar to the Gay-Lussac law, the relationship obtained on the graph is a linear graph that starts somewhere along the y-axis. Again, remember in physics, we don't like this kind of graphs, but you can't change degrees Celsius just like that. You have to find out how to change it properly. So extending this graph backwards so that we can find the x-intercept. Again, what did I say? Again, just like the Gay-Lussac law, they found that, this will touch the x-axis also at negative 273 degrees Celsius. Same number as in this law. So they found that, okay, we can make the same temperature scale adding 273. So that will be the same scale in Kelvin. And that's how we now can get a straight line through origin so that we can get just nice. And this is why Kelvin is the SI unit for temperature, not degrees Celsius or even degrees Fahrenheit. It's because of this situation where we found that based on the gas experiments, by using the Kelvin scale, we can get a graph that starts from the origin. So the relationship over here can now be expressed. I'm just going to change the words here. The volume of the gas is directly proportional to the absolute temperature, provided that the mass and pressure of the gas are constant. Now, we use the term absolute temperature over here because absolute temperature refers to the Kelvin scale. So if we look at these two laws, you'll find that at 0 Kelvin, the pressure of the gas is zero, and the volume is also zero. That's why at 0 Kelvin, it's known as absolute zero. Everything is zero. So in theory, at 0 Kelvin, the gas has zero volume and zero pressure. So they don't take up any space and they're not moving, so they're not exerting any gas pressure. Absolute zero. So I'm going to write that down for your reference. Okay, absolute zero is at specifically at 0 Kelvin. Okay, 0 Kelvin. Sorry about that. Okay. It's at 0 Kelvin, volume is zero, and the gas pressure is zero. This law was discovered by Charles, so that's why this is known as Charles' law. And that's the second gas law. Third gas law, where now we keep the temperature constant and we will observe how the gas pressure changes in volume. I realize there's a typo here, so I'm just going to fix that really quickly. Okay. And zoom in. So I want you to imagine now again, let's say we've got some gas particles trapped inside here. This time the temperature is the same. So when the temperature is the same, that means that the average speed which the particles are moving at is constant, the same. So whether it's a small container or a large container, the speed of the particles are exactly the same. So in the first box, the container is much, much smaller. Would you imagine similar to, the second gas law just now? This is a balloon or a container which can expand or shrink. And now same container, same gas particles, we now expand the container so that the volume is much bigger. So same gas particles now, still moving the same speed. Do you think, okay, how often are these particles going to collide against the walls of the container compared to the first situation? So remember, these two diagrams here, exactly the same container, same particles. The only difference now is that this second diagram, the same container now, larger volume. So think, larger volume, but same speed. How would the collision be like compared to the first? Less collisions, right? Because there's more space to travel. This has much less space, so they're going to collide more often. This is going to collide less often, less collisions, less force, less pressure. So for this situation, it's going to move it. Oh, it's not moving, it's just rotating. Okay. For this situation, we find that the greater the volume, the lower the gas pressure. So this one has an inverse relationship. So if we were to plot a graph, of pressure against volume, say pressure in Pascal and volume in meter cube, we're going to get a graph that shows an inverse relationship. So if you recall your math, let me just fix this a little bit. It's a little bit messy, right? It's going to look like this. So you actually get an inverse relationship like this. If we wanted to make this into a directly proportional graph, what we can do is we can plot this graph of P against, sorry, my iPad. Okay, let me fix this a little bit. Okay, there we go. You'll have 1 over V, which is basically per meter cube. And for this one, because of the inverse relationship indicated by 1 over V, this is how we can finally get a Straight line through origin. So for this one, the relationship, I'm just going to copy and paste because, I'm lazy. So we have, in this case, gas pressure. Pressure of the gas is inversely proportional to, well, not the temperature this time, it's inversely proportional to the volume, provided that the mass and temperature of the gas are constant. This is also named after the researcher who discovered this relationship. This is named after Boyle, and that's why this is known as Boyle's law. So these are the three gas laws that cover the properties of gases in terms of the temperature, the volume, and the pressure. Okay, now just a little bit about the formula that are related to each of these gas laws. So let's start with the Gay-Lussac law. So in this case, I'm just going to move my face out of the way because, it's blocking the space over there. Right, so based on the graph that we have over here. So we're going to refer now to the absolute temperature, not to degrees Celsius. Why? Because if you have a directly proportional relationship, it's a lot easier to develop an equation out of it. So based on the absolute temperature scale, we know that pressure is directly proportional to absolute temperature. So I'm going to write it this way. This is a math way of describing this relationship. So pressure is directly proportional to absolute temperature, which is expressed as capital T. Now, from here, if you can recall what you've learned in maths, if we were to write this into a proper equation, you cannot just write P equals T. So I'm just going to change color for a bit of, clarity and fun. P equals to, you can't write it as P equals to T. So I'm going to write it as KT. In this case, what's K? You can think of K as being the gradient of the graph. It's more correct to say that it's a constant value or a coefficient. Either way, you have to put a K there. Now, this value of K is not important. We are not interested to find out the value of K. Normally, we want to find out before and after how are the values of the pressure and temperature different. So from here, we know, okay, first situation, the pressures, of course, we call it's affecting the temperature or the other way. The second also. Now, regardless of whatever is happening here, if it's the same container, same gas particle, same everything, the value of K in the first and second situations will be exactly the same. So from here, you can write it as P1 equals KT1 if this was a first situation. And for the second situation, it will also be the same. It will be P2 equals to KT2. So from here, because K will be the same, if we rewrite this, you get K equals P1 over T1 and K equals P2 over T2. Combining them, let me just move. I realize I did not give enough space. So I'm just going to move this out of the way here. And what we will get in the end is we will get this relationship. P1 over T1 equals P2 over T2. And this is the formula for the Gay-Lussac law. So if you can understand this, the others are pretty much the same as well. So if you were to look at the Charles' law, it's also the same. In this case, now, V is directly proportional to T. So if we rewrote this, we would get, just keep it as black now, V equals to KT. Okay, if K equals V over T, now we know we have V1 and T1, right? So let's say, for example, I'll just scribble it over here this time. K equals V1 over T1 and K equals V2 over T2. Remember, the K is not important. The K is the same in the exact same situation. Now, different containers, different gases may have different values of the coefficient of K, but for the same containers, same gas particles, they will have the same K. So remember, we want to find out the properties of the gas in different situations. So in the end, we'll end up getting the formula of V1 over T1 equals V2 over T2, and this is the formula for Charles' law. For Boyle's law, because the relationship is inverse, that means P is inversely proportional to V. So this is how you write it if it's an inverse relationship. This is how you write it in maths. So putting it into an equation becomes P equals K over V, giving us PV equals K. Remember, K is the same for the same situation. So if you have P1 V1 equals K and P2 V2 equals K, because K is the same, in the end we're going to get P2 V2 did I just write 2? Sorry, senior moment. P1 V1 equals P2 V2, and this is the formula which can be used to solve questions involving Boyle's law. So these are the three gas laws, and all of these can be combined into one universal gas law. So let's just run through them again very quickly. So we have the Gay-Lussac Law, we have Charles' law, and we have Boyle's law. The Gay-Lussac law relates pressure with temperature. So that's P1 over T1 equals P2 over T2. Charles' law is volume and temperature. So V1 over T1 equals V2 over T2. Boyle's law is pressure and volume. So that's P1 V1 equals to P2 V2. Combining them all together, you find that, okay, you've got pressure on top, volume on top, and temperatures at the bottom. In the end, they can be combined into a single formula, which is P1 V1 over T1 equals P2 V2 over T2. And this is the universal gas law. So touching a little bit about the absolute temperature. So absolute temperature refers to specifically temperature in the Kelvin scale. So as you saw from the earlier explanations of the gas laws involving Charles and Gay-Lussac, you can see how this Kelvin scale came about. It was created in order to enable the calculations to be more accurate. So that way, by shifting the graph forward so that we can start from the origin, you're able to get a more accurate relationship. So this is where the Kelvin scale came about. And that is why Kelvin is the SI unit for temperature. So how do we get Kelvin again? Very simple. Just take the value of the temperature in degrees Celsius. I'm going to write that in another color just because. So usually the absolute temperature is represented by a capital T, which is in Kelvin. So I'm just going to put here bracket Kelvin. This is basically theta, which is measured in degrees Celsius, plus 273. And that's how you get the temperature in Kelvin. For example, if you have a value of temperature as 30 degrees Celsius, that means a value in Kelvin is just 30 plus 273, and that's how you get 303 Kelvin. That's simple. So if you have to work backwards, like for example, if you have temperature as say 500 Kelvin, to get the value in degrees Celsius, it's just 500 this time minus 273, and you get 227 degrees Celsius. And that's how you get temperature in Kelvin from degrees Celsius and vice versa. So I hope you found this video helpful and educational. Don't forget to subscribe for more lessons from Miss Ho. And of course, you can check out for more information on physicsrocks.com. Thanks for watching and happy studying.